Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and this is the summer 2020 offering of GPU programming for video games. Today we're going to look at a special texture mapping technique called environment mapping. In most of the previous lectures, I've shown you code and then showed you a demo. I'm going to start this lecture by showing you a brief bit of the demo and then showing you the code. But first, I want to give credit to Tom Higgins, who created this animated horse model that I use in the demo. So this is available for free from the Unity Asset Store. And you should also go check out Tom's other models. I've started up a blank Unity project in 2019.4 with just the basic built-in 3D graphics pipeline, not one of the weird, new, fancy scriptable render pipelines. I'm going to take the GPU20 environment map shaders Unity package and drag that onto the assets. I've also tested this in the 2020.1 beta. If you're using some other version of Unity than 2019.1 or 2020.1, you may need to make some tweaks to the code. Anyway, there's two scenes in here. Let me just go ahead and double click on the fanciest one for the moment. Let's check that out. And doesn't that look awesomely cool? So in this lecture, we'll see how to create these reflection and refraction effects. Notice that we'll be faking these effects. If you want reflections and refraction, and by refraction, I mean you're actually seeing through a translucent surface. If you want an accurate simulation of those kind of effects, you need to go to something like ray tracing. And although the latest graphics cards have some built-in ray tracing capability, there's not many games that use them because not a lot of people actually have those cards. And even the games that use them typically only use that real-time ray tracing capability for some particular aspects of the graphics, and they'll use the rasterization model for everything else. So we've made extensive use of the normal vector of the surface being lit, the vector pointing from the surface to the light source. We haven't really yet used the vector pointing to the eye a great deal, other than to talk about spotlight effects. This is going to play a critical role in specular lighting calculations that we'll look at in a future lecture. The specular lighting calculations will also make extensive use of this half vector, which is the vector halfway between the light and the eye vector. In this lecture, we're going to make great use of the reflected vector. Now, this concept of a reflected vector is a fairly general one. Here, it's described as reflecting a particular light vector. What's a little bit confusing is that in this lecture, we're mostly going to want to be reflecting the eye vector. And instead of working out all of the trigonometry here, I'll just state the way that this is usually formulated. So you can give this formula the normal vector and this incident vector. Be careful with the sign on this, and it will give you the reflected vector. And fortunately, there's a command built into most shading languages that implements this formula for you. So the way we're going to fake reflection effects is with the use of a cube map. So you can imagine going out into the world with a camera and pointing the camera ahead of you and then behind you and then towards the sky and then towards the floor and then towards the left and the right, and building up a series of photographs. And there are a bunch of folks who've made a hobby of this. It takes a lot of post-processing work in something like Photoshop in order to get the seams between the images to make sense so you don't get abrupt transitions. And what we'll be able to do then is use that cube map to fake this cool reflection effect. Now, the reflection that we're seeing depends on the eye position. So this is something new. This isn't something you can implement using the diffuse kind of lighting that we've been looking at so far, because that doesn't depend on the angle of the viewer. This is a special case of a specular reflection, essentially a perfect specular reflection, a perfect mirror. In a future lecture, we'll look at some much more complicated specular models. Just like you use Tech2D to look up points in a standard 2D texture image, you can use TechCube to look up points in a cube map. But instead of a 2D value, you give it a vector pointing towards the cube map, and then the hardware will figure out both which of these 6 images that vector would intersect with on the cube map, and also the point within that particular image. So this is very convenient. One interesting thing about this vector doesn't need to be normalized to have a length of 1. As long as it's pointing in the correct direction, it's fine. To once again give credit where it's due, the demo scene I created is using this cube map by Emil Persson. I'm not sure I'm pronouncing that correctly. I'm probably not. Anyway, this is a cube map they created of St. Peter's Basilica. And as you can see, it takes a bit of work to try to make sure that this somewhat sensibly matches up along the various transition points of the cube map. In addition to reflection effects, we can also use cube maps for refraction effects, where we're imagining that the object is translucent and we're seeing light waves from things on the other side, but they're distorted a bit because those light waves are being bent as they're going through the surface. So if you go back to your physics lessons, you'll find that there's the concept of an index of refraction, and then Snell's law gives us a relationship between these angles of the light coming in and then the light going through the other side in terms of the index of refractions. For what we need to do, we don't need to know the exact index of refractions. We just need to know their ratio. And so we'll place that into the refract command. You give the refract command an incident vector. Again, that's going sort of opposite the direction of our usual vector, the way we've defined it, and the normal vector for the surface, and then it will give you this refracted vector. I'm not listing all of the mathematics here, but you can go look that up if you're wondering what the exact formulas are that refract is implementing. So here are some examples created by Thomas Kerwin at Ohio State. Here we can see an example where you have these floating spheres, and if the index of refraction of the material making up those spheres is larger than that of the air that we're looking through, then you have this effect where things on the other side basically look bigger. Whereas if those spheres are made up with an object whose index of refraction is smaller than that of the air, then the things on the other side look smaller. As we can see, air has an index of refraction pretty close to a vacuum. Water is higher, which is why things look distorted if you're looking down into a pool. Glass and plastic are a little bit higher. Diamond is extremely high. So let's take a look at the code. The first piece of code I'm going to show you uses a per-vertex approach for some of the calculations, and we'll see this isn't very good, so we'll very quickly move towards a per-pixel approach. But I wanted to show this to you first to make the point. So we're going to give it a cube map. We've previously seen textures as being listed as having a type 2D here, but these are cube maps, so we say cube instead. Here's a slider for the eta ratio. For this shader, I created a crossfade slider that lets you crossfade between a pure reflection effect and a pure refraction effect. The rest of this is the sort of stuff we've seen before. As usual, it's not sufficient to just declare these variables in the properties list. You also have to explicitly declare their types in the shader code itself. So instead of sampler 2D, this is now a sampler cube type. The information we're passing in for each vertex is just a position and a normal. I left out all of the 2D texture mapping stuff just to focus on the cube maps in this lecture. So in the vertex shader, we're going to compute reflected and refracted vectors in the world space coordinates, and then let the interpolation hardware interpolate those, and then parcel those out to the individual pixel shader calculations. So taking a look at the per-vertex version of the code, the vertex shader has a lot of stuff we're used to seeing. We've seen over and over the transformation of vertex positions from object space into world space, and then the continued transformation into clip space through the view and the projection transformations. This coordinate in clip space is used by the GPU hardware to figure out where pixels on the screen should go, regardless of whether or not we use that information in the pixel shader. We transform the vertex normals into world space, and remember that transformation is a bit weird. You need the inverse transform of the upper left 3x3 portion of your transformation matrix, which we facilitate here by using the world to object matrix provided by Unity, which is the inverse of the object to world matrix, and also using the trick where we're thinking about the normal vector as a column vector, but by placing it first in the multiplication command, we wind up facilitating an effective multiplication by the transpose. So all of that is code we've seen repeatedly in previous shaders that we looked at. We're also going to compute a incident light vector that's pointing from where the camera is to the vertex. This rolled space camera position variable is filled in for us by the Unity runtime. If you're writing your own custom engine, you would need to have a piece of code on the CPU side that fills this in for the GPU. And then we use the reflect and refract command to find the reflected and refracted vectors in world space coordinates. So we compute these reflected and refracted vectors per vertex, and then the GPU hardware is going to interpolate these vectors when deciding what to pass off to the various bits of hardware that are running the pixel shader code. So the pixel shader itself doesn't need to do very much. It takes the reflected world space vector and looks that up on the cube map. And then it takes the refracted world space vector and looks that up on the cube map. And I've set it up here to linearly interpolate between those two colors it looks up, depending on what this crossfade variable is. So if it's all the way to one side, we'll get a mirror. If it's all the way to the other side, it's translucent and trying to look towards the other side. By the fact that we were computing these vectors for each vertex and then just linearly interpolating between them, that creates some problems with some clearly visible artifacts. Before we try to build a per-pixel version of the shader to deal with those artifacts, let's take a look at what these actually look like when the game's running and not just still frames, because it's even more dramatically noticeable there. So here I'm running the per-vertex scene. All of the objects are using the same material, so I can play with the parameters on just one of them. Let's play with the crossfade first. So setting it to 1, we have entirely refracted light, and if I set it to 0, then we have entirely reflected light. Obviously, when things are reflected, changing the eta ratio doesn't change anything, but if I switch back to being perfectly refracted light, now I can change some things. So here's a very small eta ratio. Here's more of a medium eta ratio. Notice that the objects here are pretty close to invisible. It looks kind of like the Predator invisibility effect from the Predator movies. Let's now make this really high. Oh, look at that. That's just crazy. Okay, let me make it not so extreme. So the main thing to notice is that even if you don't pay any attention to this weird little bar on the outside here where the calculations are freaking out, you can definitely see this weird gem-like effect where things are sort of blinking in and out. And you can really see this flickery effect on this little ellipsoid that's going back and forth here. Let's see if I can still see it if it's less extreme. So even here, you can see, see how it goes blink, 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 blink. That's kind of a aliasing effect. Blink, 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 blink. Basically, doing per-vertex lighting isn't giving us enough detail in those reflected and refracted coordinate transformations. So the reflected's not quite so bad, but definitely the refracted is a mess. And I could set this to be something like 0.5 to be a combination of the effect. There's that blinking again. So per-vertex is definitely not the way to go. One thing I want to point out before we go on is that notice we didn't bother putting any normalized commands here. Usually you can't expect that the interpolated normal created by the GPU hardware is going to have unit norm because the GPU doesn't know that's what we're wanting to do. So we have to normalize these vectors ourselves in the pixel shader. But here, the TechCube command doesn't care if it has unit length or not. All it cares about is the direction. So before we look at the per pixel code, I want to talk about an effect that I added to the per pixel code, which I didn't bother to add to the per vertex code because the per vertex code wasn't performing very well anyway. Now, the equations that I'm showing you here for the Fresnel effect aren't at all related to the actual physics. This is a quick and dirty way of getting some Fresnel type effects that I pulled out of the CG tutorial. We'll look at some more precise Fresnel effect equations in a future lecture. This is just to have something that's easy to implement. The idea is that the amount of light you see from a translucent surface that's actually passing through the other side versus how much you see reflected depends on the viewing angle. So if you walk up to a swimming pool, but if you're some yards away and you're looking at it at a fairly shallow viewing angle, you'll mostly see the sunlight reflecting off the pool. But if you walk up to the edge of the pool and look down, you'll see less of that reflection and more of what's actually inside the pool. And so this is a quick and dirty way of getting that kind of effect. Remember that the incident vector, for whatever historical reason, is defined as being opposite of our usual I vector. So I is pointing from the camera to the surface instead of the other way around. I'm not going to bother slogging through all the details of the formula here. Bias, scale, and power are parameters you can use to adjust this effect. But the net effect is that you get a reflection coefficient that's between 0 and 1 that you use to interpolate between the reflected and refracted colors. And this formula is set up so that if the incident vector and the normal vector are lined up, so you're looking at a surface square on, you get strictly the refracted light. But as you move away from that, you're seeing more and more of the reflected light. So let's take a look at our code. Here I've added 3 new parameters for the Fresnel effect. And I've also added a couple things we haven't used before. I've added a toggle and a keyword enum. These are Unity-specific things, but pretty much any engine in the same class as Unity will have similar facilities in some way. So toggle will actually create a little checkmark box that will be filled with either 0 or 1. Here it defaults to being unchecked. And this is what I'm going to use to select a certain diagnostic mode that ignores all of the cube lookups and just replaces them with the color blue and yellow. This will give us a way to visualize the Fresnel reflect coefficient calculation. And then I have the keyword enum that will let us switch between using the original crossfade I already used in the Per-vertex shader and the fancier Fresnel effect. By setting it to crossfade, it makes it easier to see what's happening with the reflections and the refractions versus the Fresnel mode that is going to mix them together. When you have the Fresnel mode activated, then it doesn't use this crossfade value at all. Enumeration here lets you select things from a drop-down menu, so that will let you label things. So the way that you actually use these toggles and enums is by placing some pragmas into your shader code. So the toggle is activated according to this shader feature line, and then the multi-compile thing will handle the drop-down menu that you have here. And these names have to be hard-coded like this. So here we have blue yellow with an underscore. So we need a shader feature called blue_yellow. It will want to see it match like that. Similarly, for the multi-compile, you'll need to have a couple of things in all caps here that are this blend with the underscore here. You don't use the underscore here. I know that's confusing. Anyway, you have blend here with the underscore, and then you concatenate it with underscore, these various options in the drop-down menu. Again, the letters here have to match for this to work. This is a Unity-specific feature, but again, nearly every other engine at a similar level of sophistication as Unity will have something like this. So most of this is the same as what we've seen before. Of course, I do need to add these declarations for the Fresnel parameters. The main thing that's different here is that instead of passing along the reflected and refracted vectors that were calculated in the vertex shader and sending that to the interpolation hardware, here I'm sending something more primitive earlier in the stage. I'm just sending the positions and the normals because we're going to use that now to do the calculations in the pixel shader. So, as you should expect by this point, moving from a per-vertex to per-pixel approach results in the vertex shader becoming a lot simpler. We still have the geometric transformation for the positions of the vertices, and we have the transformation of the normals, but everything else has moved out of this function. So all of this is fairly standard. This is more or less the kind of vertex shader we saw in the per-pixel lighting approach to basic diffuse shading. So as expected, just as the vertex program became simpler when we moved to a per-pixel approach, the fragment program became more complicated, but not in a complicated way. These lines where we compute the incident and reflected and refracted vectors in world space are exactly the same code we saw in the vertex shader in the per-vertex version. We just cut and pasted that code. And then I do the lookups into the cube maps. This is code that was in the original pixel shader for the per-vertex version of the code. Here I compute that reflect factor with the equations from a couple of slides ago. Again, this is a hack from the CG tutorial. We'll look at more elegant things in a later lecture. And then here, for the first time, I'm using these check marks and these pull-down menus. If the blue-yellow option is checked, then I just ignore whatever the cube map lookups are and replace those with yellow and blue. And so if I have this checked, the refracted color is yellow and the reflected color is blue. So this is very useful for visualizing how this formula for the reflect factor works. And here we implement the effect of the drop-down menu. So in those pragmas, we stated that we had a blend crossfade and a blend Fresnel. And then we use this define set in these if-then sort of meta language that is on top of HLSL. One or the other of these will be quote-unquote defined based on what the user selected in the Unity inspector. And I should emphasize all of these parameters, including these check marks and the drop-downs, these are things that you can change via the C# script. So you can put in some pretty complicated behaviors if you want. Here we'll just have the user click on it. And so here we're lerping between the reflected and the refracted colors based on either that primitive crossfade fader or that complicated fake Fresnel effect reflection factor. So let's see what these wind up looking like. I'll show you the actual running demo in a moment, but first I want to show you some still frames just to emphasize certain points. So here's an illustration where we're using the crossfade slider and having it set all the way to refracted. And here you can see the various effects. And so it's a pretty complicated effect. If you're wondering about this little band here, this is something that happens when you have a pretty big iteratio. And basically, this is the point where the calculations are just breaking down entirely. So here's what that scene looks like for a fairly low iteratio. Here's what it looks like at a medium iteratio. And here now for a big iteratio, it's essentially having this squishing effect. So it looks like there was a person standing here, and now you can see them in this little globe. And again, these are sections where the calculations just numerically break down. Now here's an example of clicking that yellow-blue option to visualize the Fresnel effect. So on the left here, we have a combination of seeing reflections and refractions, which is visually very intriguing, but it's kind of hard to play around with these sliders and get a handle on what's actually happening. Here, we have this blue and yellow business going on. So wherever you see blue, that's pretty much pure reflection. Any case you see yellow is pure refraction. And when you have a bit of each, those will blend and become gray. So you can play around with these sliders and get a much better sense about what that formula is doing. So here we do have a combination of reflected and refracted light. But by putting it in this visualization mode, it's a lot easier to see what it's actually doing. This particular face here, that's going to be mostly refracted, but this face here on the cube is mostly reflected. So I've loaded up the per pixel scene. Let's turn the crossfade all the way down to get a pure mirror effect. I need to switch the blend mode to crossfade. So here I have a pure mirror effect. And now let's switch it back to having a pure refracted effect. Let's change the eta ratio to something relatively small. Okay, that's fine. Let's make it something big. So notice that we still have this weird part where the calculations are breaking down, but you now don't have that weird blinky gem-like effect near the edges. Let's make this a little less extreme, something like that. You don't see the blink, 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 blink temporal aliasing kind of effects we saw with the Per-vertex version. Let's switch this back to using the Fresnel effect. So I have a variety of things I can change here. What does Fresnel bias do? So that does something. Here's the scale. Here's a scale of 0.2, a scale of 0.9. Here's 0.5. What about the power? So there's 0.1. What about a power of 10? Okay, so I really have no idea what these parameters do. So let's click on this blue-yellow. So now I can really look at the effects of these parameters directly. So here it looks like it's mostly gray, so we've got a pretty even mix of both. What about this scale here? There we go. So putting the power above 1 just blows everything out. Here's 0.3, 0.1. This is the kind of thing you can get with a specular spot, but it's not as, it looks kind of like a specular spot, but it's not. It's this sense of what we're seeing through the object and what's the reflected part of the object, sort of changing how that transition works. I'm just playing with the scale parameter. I think that's min-maxed out or something at some point. What about this bias parameter? Oh, that's fun. You can play around with these different parameters and see how they affect this transition from seeing through the object to just seeing reflections. Notice in the crossfade mode, this setting's useless. You have to have it in the Fresnel mode. Go back to regular. There's one more interesting effect that I'm going to have you do as a homework assignment, and that's to implement chromatic dispersion. Basically, we're going to give red, green, and blue different indices of refraction. And this is what happens in materials that give you a prismatic effect. So this lets you build prisms. Now, if you wanted to be super accurate about this, you would want to actually split the color band into a wider set of colors and maybe give something like orange or purple their own index of refraction, but nobody actually does that. That's getting a little overly detailed here. At least nobody does that for real-time rendering. There are offline renderers that do highly detailed spectral calculations.